All right, welcome to today's Ascendo Reliability webinar. This is Fred Schenkelberg, and I wanted to talk about some of the critical concepts. And given my little trouble here in the first 2 minutes of having everything all set up and then something crashed and not having a backup ready to go, I've been doing this for on close to 5 years through Ascendo, and yeah, we've run into a range of different issues over time, and it just highlights one of the key concepts is that everything fails. Everything that we can make, everything that's in nature, everything at one point or another will fail. And by failure, I mean doesn't perform as expected, doesn't perform in a product or a system or an item ceases to function. For example, it would be a generic or a broad sense of what a failure is. Now, we could have an entire webinar just on how do you define failures, and especially when you have no trouble found or no fault found kinds of issues, as to what exactly is a failure and what counts and doesn't count. Here I'm using the term failure very, very broadly. And eventually, as you know, the sun will burn out. It will either, I don't think it's going to supernova, I read that someplace, but it will cease, it will run out of fuel, it will die. Um, that even that steadfast system that will last for billions of years is going to fail. And once that fails, pretty much anything that we make on the Earth is going to stop functioning also, or cease to operate at some point. Although I have heard that the Hoover Dam is going to run for a long, long, long time after everything else is gone. So unless there's a major catastrophe to those systems, it's pretty robust, and they expect that to last long past everybody else. Now, in reliability engineering, the work that we do is often really aimed at, well, how do we know this thing or item or system is going to last long enough? And so we often are working on, well, how do we design something or maintain something so we can skip the failures for now or minimize the failures for now, mitigate them in some form or fashion. And that's a key tenet of what we do is we deal with failures and trying to push them off, right? But we also have to focus on the basic premise of what we do in dealing with failures is that we have to understand them, right? And we have to understand the systems and the people and the decisions and all of the elements that come together that allow us to push off or delay these failures or minimize or mitigate failures in whatever we're working with. And by doing so, that's how we add value to an organization. We bring a unique perspective to an organization with a focus on failures that few others actually do, right? Now, I'm going to caveat that because Henry Petroski, one of my favorite authors, in one of his books where he's looking at the history of engineering, essentially in a large context, it makes the statement that most designers, most engineers design away from failure because they want their system to work. They want their product to work. And I truly believe that. I've seen that over and over and over again. Yet a mechanical engineer may understand some failure mechanisms, may understand material strength like a material scientist does and incorporate that into their design, but may not fully understand the range of types of failures that could occur for that particular system. And that's where the depth of knowledge of a reliability engineer steps in and assists that mechanical engineer into creating enough understanding of what could fail so that they can design appropriately. We supplement what they're doing in order for the design to work. So here's a question for you while I grab my first sip of water here, is in the questions tab, can you answer this question? Are failures good or are they bad? And you can use whatever perspective you'd like, if you're testing or if you're a customer or if you're a design engineer or an operations manager or wherever you are. How do you, what's your view of are failures good or are they bad? Evan's spoken like a true statistician or engineer. It depends, right? I agree with that. Let's see. They failures are good that provide a livelihood for engineers. Yeah, and you've probably heard me say this: is it keeps everything fails. Thus, we have job security. Eventually everything's going to fail. Max, I like it. Good failures equal learning. We're going to circle back to that quite a bit later. Ganesh, many people consider failures bad, and well, I'm going to challenge that a little bit as we go forward. Andre, good in the sense that you get data points, yeah, and that's a good point. You can have a lot of failures with absolute no failures, and it's hard to judge exactly what you're learning there. We learn from them. They provide an opportunity to learn. Early stages, it's great. Yeah, good learning opportunities. Good so long as it doesn't hurt people. Yeah, keep it safe. Good is keeping engineers in a job. All good, right? So I think this, I'm speaking to the choir here, is kind of the add here. Now, for some of you, I mean, failures happen, always happen, all right? And I like the first answer, Evan, is it depends. If it fails and it's unsafe and it harms our customers or society in some way, well, that's not a good thing. Yet it will happen. There's a finite probability that all systems will fail at some point or another. And many of our products, and you probably have a lot of experience yourself with products that did not work as expected or failed to function, just like my startup today of getting my browser to show the slides failed for me. Now, the consequence of some failures is pretty significant, and those are typically what we consider a bad failure. If we yet, even given a catastrophic failure, if we can learn something, if we can alter our designs and our expectations and our knowledge about how things fail, it provides some information for us so we can still learn from all failures. It's just more painful at some points in the life cycle of a product or a system. But one of the key tenets, one of the basic functions of reliability engineering is that failure happens, right? These things are going to happen, and if we manage that when it occurs, we can learn enough to do our second key function, is to mitigate them or postpone them or delay them. And so if you've listened to any of my podcasts before and many of my webinars in the past, I've talked about failure mechanisms. Now, I know firsthand in doing FMEAs that many people confuse a failure mode, MODE, with mechanism, the process. I want to be very clear what I mean here. The failure mode is a symptom. It's what a customer experiences. For me, it was my display software for this slide set today didn't work. It wasn't showing the slide deck, and I had to restart that part of the application. That was a failure mode. My symptom was it wasn't showing the slides when I wanted them to be available. Or you turn the key in your car and it doesn't start. Those are symptoms that something has gone wrong. But using the car as an example, it could be that it's the wrong key and it won't engage the starting function of your car, or the starter has failed, so it doesn't turn over even though it has power. The battery could have failed, and or some other element of your system, like no fuel in the system, or somebody took the motor out of your car and there's no motor there whatsoever to even start. I mean, it could be a long list of reasons why it doesn't start. Now, looking at just the battery, the failure mechanism could go further than that, that the battery is drained. Well, why is that drained? Now we're getting into that 5 whys kind of a process. And at some point, there could be, we left the door ajar, and so the dome light was on and current was draining. And so the battery is depleted because there was a small current drain for a long period of time, right? Or it could be another why. Well, why was the door ajar, right? Well, there was debris in the door that didn't let it latch, or it was a human error that I didn't notice that it wasn't quite latched all the way and the light was off. And so it was that. And then why was that? Well, I was distracted. And you could go on and on and on with that. And typically a mechanism is down to where it's some fundamental phenomena, a physics or a chemistry or a human decision that led directly to that failure to occur. So a mechanism in my mind for most of what we do is the physics and chemistry of what's happening. It's not the symptom that we see, it's the underlying initiating cause that does it. So if I alter, say, making sure that I pay attention to when I close the door, which I usually do after I get a dead battery and notice that the door was ajar for a couple of months, I can avoid that problem. I have learned something and I can avoid it. If it was actually a bad chemistry in the battery had worn itself off from too many charges and discharges, or it was cracked and the battery fluid had drained out, then there's other rationale down to a mechanism. Was it mechanical damage to it? Was it a chemical depletion of it? Whatever it was. A lot of what we do in dealing with reliability work is understanding the mechanism. We can solve mechanisms, right? We can solve elements that are in the physics and chemistry world. The human ones are more difficult. We can alter systems or create elements that alert people that something's not correct. Those are all possible. But the underlying fundamental mechanisms and our understanding of those is what allows us to work with engineering teams to solve those problems. And that goes back to what Henry Petroski talked about, is that engineers tend to design away from failures. Well, that implies that we have to understand those failures. And in deeper into that is we need to understand the actual what's going on that causes that failure to occur. One more example, let's say it's corrosion, right? Oh, now I'm drawing a blank on it, the example I wanted to use. If I have a corrosion that requires some kind of solvent or ionizing type fluid, we have some metal, say a copper, for example, and we need some voltage. Electromigration, that's the term I'm thinking of, which will cause a short between various polarities of traces by growing a copper strand between the two of them, causing a short. But it requires that electric field to drive the copper from one potential to the other. But it also requires a little bit of a solution to dissolve, essentially, release the copper so that it can move and create these beautiful looking trees as it finds a path following the current or the voltage gradients to create a short. But understanding that mechanism means that we need to have metals that are susceptible to dissolving, essentially, in the right conditions, something that causes the dissolving, some solvent or solution of some sort, and we need the voltage. And so by understanding it at that level, we can separate the traces further apart. We can reduce the voltage field, the gradients that are causing the growth. We can change the metals. We can encapsulate them. We can prevent the contaminated solutions or solvents from getting on these systems. But given the fundamental understanding of what's happening, it gives us many, many options of how to go solve it. Now, of course, some problems are harder than others. There's no worries with that. But when we are faced with a problem or a failure, there's one approach that I've seen so many people use, and it's one of those early tenets we learn about in failure analysis. And I call it the ready, shoot, aim approach. It's where you get 3, 4 people in the room, you've just learned about a problem, and some engineer says, oh, I know what to do with that, and runs out of the room and says, I'm going to go implement this solution. That's a ready, shoot, and then they go sort out whether they're actually solving the right problem or not. Now, sometimes they actually get it right? They solve a problem, and we all consider them geniuses and heroes. But many times they don't. The presenting symptoms don't always give us a clear picture of what the problem is. So having the discipline to describe the problem, to gather information about it, to do the experimental work, to fully understand the underlying mechanisms, then allows us to implement a solution. And I heard many years ago, one way that one way to tell if you understand the failure mechanism is that you can turn it on and off, right? If I understand it well enough to know that if I add this particular ionic solution, this chlorine ions to this mix, that the electromigration happens. And if I take away that contaminant, then it doesn't happen. I understand it well enough now to know that that's one of the key elements for that piece of corrosion. And that's a simple example, but the idea is with this 8 disciplines or plan, do, check, act type processes is that we focus in on understanding at as fundamental level as we can, such that we can turn on and off this particular mechanism. It helps us to avoid guessing. It helps us avoid try everything and hope something works. It focuses our work on both learning and then solving the problem that actually is at play in our particular situation. So the key part of, I think, of what we do as reliability engineers is implement this disciplined approach. Is that, and it's aimed towards understanding first, then solving. Now, of course, we fight all kinds of barriers to doing that. Is we need to get the line up and running. We need to get this product shipped. We need to reduce the cost. We need to, we have a potential solution. One of these solutions will probably work. Let's try all 3 and save the time it takes to investigate it. The culture that we face in many organizations doesn't allow us or give us the privilege of going off and learning from failures. The other part of the culture that I really don't like is when the organization blames people for a failure. And I hope you don't work in an organization like this. If you say, hey, I noticed this isn't working correctly today. What are we going to do about it? And either you get tasked with having to go solve it. So if you're already busy, you don't mention any more problems unless you really need to solve that problem. And another issue is that you get, well, it's your fault. If you found the problem, it's your fault. And you get a bad rap or looked down on for talking about failures. And you see this in FMEAs where people won't want to talk about how a product will fail, even when it's a process that is deliberately trying to figure out how it fails. It's just not safe to talk about it. And that's a cultural issue. Now, what I advocate is that every failure, and I saw that earlier in the messaging, is that every failure provides an opportunity to learn. We ran into a barrier, we ran into a hurdle or something either that we suspected, this flange can only take so many foot-pounds of pressure or force before it fails, before it deforms. And that confirms what we knew in the design process. So we have plenty of margin. But if it failed at half the rated load that we wanted it to carry, we learned something that one of our assumptions was wrong, or one of our figures in the calculations earlier for the design was wrong. And we learned something. We can deal with that. So there's plenty of ways that the culture around us affects how we are able to deal with failures in the product and either design them out or address them or go after them. Part of what we do, another key tenet of what we do, is shaping that culture, making it safe for the entire organization to talk about failures. Yeah, and just checking out one of the comments here. It's a good point. Is oftentimes we're looking for potential failures and we don't see them, but we have to be prepared to be surprised. So there's things that we look for, then we're absolutely looking for, say, that electromigration, and it's occurring. But let's say we get some other completely different failure, say an electrolytic capacitor explodes. Euphemistically, it's called venting. Well, what went on there? Is there some other phenomena at play here that's causing the overvoltage for these parts, or was it a bad part? Let's deal with that. The issue is that the greater part of the organization is going to guide or manage how we go about dealing with failures and how much time or much effort we go into doing failure analysis, but also on how we think about and treat, say, a prototype failure. A simple example is 1 in the 10 prototypes doesn't start up. And if that's just quickly dismissed as, well, it's a prototype, they're quickly made and it's not a finished design, so we're not going to worry about it. Well, I think that cultural element there is, one, we're wasting 1/10 of our resources building a prototype that doesn't work. So let's at least learn from it of what happened. Why did that fail? Oftentimes that's a precursor to things we're going to see when we ramp up into the production and use this system. Otherwise, it doesn't always pan out, but if we don't look, we're going to see it later if it's there. And if it is just a phenomena that affected just uniquely to that prototype process, well, we can improve the prototyping process, and that has value also. And so keep in mind that the cultural element around how we think about failures is a part of what we do. We set the example of how to mine the gold that comes out of failures. All right, so here's another question for you. How do you reward failure prevention? Right? And I ask it this way because there's plenty of reward systems in organizations for when you deal with a failure. There's a big customer that has reporting a field failure and they want it solved, and 10 people jump on airplanes and half the team redesigns it over the weekend and you solve it and everybody's recognized and they're patted on the back and given parking spots and so on. Well, how do you reward failure preventions? Thanks, Todd. That looks kind of like an honest answer. Not very well. Yeah, I mean, from a financial point of view, failure prevention is we didn't spend the money on warranty. We didn't spend the engineering time resolving a problem. And isn't that what we're supposed to do anyway, is avoid problems, right? It's a good point. It's not obvious, oftentimes overtly done. Hero of the day type. Yeah, sorry to hear that, Andre. Um, yeah, Atlanta Attaboys. Yeah. I mean, sometimes it's as simple as doing that. It doesn't have to be an expensive thing. It doesn't have to be a bonus structure. It's part of what we do as a job. But the trouble is, and this goes way back to In Search of Excellence by, I think it was Tom Peters, if I remember the author's name right. And he talks about that oftentimes our management systems are set up to find people doing something wrong or a product that is out of spec. But we often don't pay attention to when something is going well or when somebody does something right. For example, in SPC, we often use the rules to look for an out of control circumstance. And we often forget that out of control circumstance may lead to an improvement in a process. But we have to pay attention to that it's not always a bad thing when something is out of control in an SPC process. It it often is, but it may well point to an improvement. We ran in inadvertently, or somebody did something that improved the process. Well, how do we capture that? It's hard enough to do in a process control setting, but when we're dealing with engineering teams and people taking the initiative to avoid or prevent a problem, sometimes just making it visible and recognizing them with an attaboy or with a pat on the back or recognition of some sort is enough to reinforce that process of doing it. It's catching people doing what they're supposed to be doing and doing it well, and then highlighting those traits. In a failure avoided actually saves us money. It does show up on the bottom line. And so we can calculate the value of doing those things. It just is, it's more difficult. That's all. It's easy to count how much it costs when 10 failures come in the door, because we can tally up how much it cost our organization to replace that unit, repair it, or do whatever. But if those 10 units didn't show up, how much did that save us, right? And where did that money go instead? And so that becomes more invisible. And I think part of what we do is making sure that the things that are in line with creating a reliable product should be recognized and highlighted. Yeah. Now I've seen this before, Maximilian, is where the design team is the ones that actually see the field failures. And so it's in their own personal interest for time management to not design it well, so they don't get distracted later in the next design by having to solve problems on the previous product. That can work in some circumstances. It also can be, well, I really like fixing problems and I get recognized for fixing problems after the fact. You have to balance out exactly how that reward system or that culture is. Maybe there's value in the firefighting process, but if you just design it well, you don't get any recognition. And that's something to be aware of. Good comment. Let's see, do this. Very low spending and failure prevention. And preventing problems is actually a really good return on investment, right? It costs us way less to deal with problems and avoid them than it does to replace the product or do emergency repairs, or especially when a line is down or a significant problem occurs and we lose market share, for example. The idea is that return on investment has to be made visible, right? And both at the interaction of people actually taking steps to do it and showing them how that makes a difference in that organization, but also in a financial setting, right? How do we quantify the contribution of prevented failures, right? If we're currently running along at a 5% field failure rate and we take some preventative actions in our next design, and we come in at 4% field failure rate, well, we proactively change the failure rate. Now it becomes dicier because oftentimes we're building off of what we learned from the previous field failure, so it could be considered reactive. Yet, when we bring on a new technology or we bring on a new component or type of design element, and we don't have the field history for it, we can still do preventative work to show that if I add this margin here, I reduce the potential of failure by this amount, and the cost per failure times that in our volume allows us to calculate out what cost we just avoided. Now, it never actually gets realized unless you do the experiment both ways. You leave that fault in and you take it out. Most of us don't want to take that level of experimentation all the way through. Yet I think articulating how important it is to do something like stress strength calculations or derating, or addressing issues we find in the design process, allows us then to prevent actual costs from occurring in the future. And for every dollar we save in warranty is a dollar back into profit. A lot of organizations appreciate that kind of logic. So we'll talk some more about that later. All right. Now, one of our roles in reliability engineering is based on that we're rarely in a position where we can say, no, that's not going to work, don't ship it, and then it won't ship. We rarely are in a position where we have control over the process, right? We can contribute uh, concepts to the product life cycle. We can contribute information and material to the design teams as they make decisions. We can contribute checklist items and questions to ask selected vendors before we make a decision on which vendor to use. All of those kinds of things allow us, are really our ability to influence other people, influence their decisions. Now, the hard part is that we can set up a report, or we can do an analysis, and we can create a beautiful field data analysis or do failure analysis all day long. But if nobody actually uses them to do anything, then we have very little influence. We may have checked off all the things we've been asked to do and still have little to no influence. And so a key talent, another one of these key concepts or tenets, is that we recognize that we're in a consulting role, right? Which means that we need to know what we're talking about. We need to do the research and the homework and the experimental work and the hitting the books, so that when somebody says, what is this happening? Why did this fail? We can say, well, that was electromigration. Here's how it works. Here's the references for it. Here's how we know we can control it. Here's where the source of these various elements come into play. And here's our options to solve it. By understanding problems well enough to help people design them out of a product builds trust in our recommendations. And it's every step of the way, every interaction we have to guard ourselves on providing information that is actually helpful. It's not one thing to say, oh, that's electromigration, deal with it. They may not know enough about it. You can save them a lot of time by contributing that detailed information about the failure mechanisms and provide options. We oftentimes have this engineering title in our nameplates as reliability professionals. Well, we get to play in all kinds of different engineering fields. We're not going to be the expert mechanical engineer and material scientist and failure analyst and statistician and so on, all these different fields that we get to work with, and software engineering and so on. Yet we can learn enough to be a contributor in all of those areas. And part of that is hinged right back to understanding failures. And so that's what I mean by do the homework and research and the math, is it enables us to contribute to the engineering discussions to find solutions. And by doing so, we gain trust. And having the trust of your organization allows us to influence at greater and greater levels. Now, you can blow that completely by providing guidance or information that is just plain wrong, and you'll have to start all over if you even get a chance to start over. So it's contingent on us as engineers knowing what we're doing and paying attention to what we're doing, and with the focus on, this is the key part, it's not just doing what we're told, go run this experiment or go do a HALT test. It's making sure that that HALT report, for example, is understood and used. Hey, this lead on this capacitor broke off in the HALT testing. It has too much mass up high, and in application or in transport, we're going to see this level of vibration. Here's the finite element analysis that shows the amount of deflection that this mass at this height has, and here's the metal fatigue phenomena that occurs in that lead that causes the problem of cracking and opening that lead. It's that level of detail that we need to go to over and over and over again. But it allows us then to influence decisions within the organization. Now, a number of years ago, I was telling a story about how this electrical engineer I was working with really didn't appreciate me showing up. And it was my fault. Every time I showed up, I was telling him how his design wasn't going to work. I was either doing testing that showed that this failed or that failed, or I was showing them how we can't manufacture that in a successful way, or whatever. And so he just really didn't like me showing up. And we were working in cubicles, so it was hard to avoid me. I just stand in his at the entrance to his cubicle, and eventually say, "All right, what problem did you bring me today?" Now that didn't create a very good working solution or relationship between the two of us. And the the change was one time when I recognized his frustration. I says, "Well, how can I help you?" He says, "Well, you're bringing me failures, but you're not bringing me solutions." Well, I don't know how to solve these things. And he says, "But you can bring me enough information about this failure, not just the symptoms, but the mechanisms. Why did it fail?" And that allows me then to do something about it. And years ago, I was relating that story, and a colleague of mine said, "Well, you have to realize that you're approaching the world from a failure space. You look at it," and they was telling the story. It makes it difficult. Being a reliability engineer makes it difficult to get on an airplane. I used to fly a lot up and down the West Coast, and it was always a 737, not the Max version. It was well before that. And I turn it right inside the door. You turn around, and up above that door was a little placard that showed the age of the plane. Its tailed, its serial number essentially, and when it was put into service. And these planes were starting to get older than my kids. And it was like, okay, how long are these planes supposed to be able to survive as a frame? And is this wing going to stay on there? Everything I look at is through the lens of it's going to fail, and can I trust it? Now, I fully realize that flying is way safer than driving to the airport. Yet, right, stuff makes the news, and I consider it when I'm driving, is making sure my car is well maintained and making sure I drive defensively and all those other things. But we tend to look at the world through a failure space and lens. Whereas the mechanical or this electrical engineer I was working with, he wanted to create a design that performed the set of functions that were in the requirements. He wanted it to be successful. The program manager wanted it to be successful. The customer wants it to be successful, right? Failures were deemed as a bad thing, and success was what we're aiming for, what we're shooting for. And it's just a different view of the world, which is fine. They're complements of each other. Yet we can change our language to say that it's 98% reliable over 2 years, as opposed to say it's a 2% failure rate over 2 years. It has exactly the same meaning, right? 2% will have a probability of failing over 2 years. It's a complement. Yet when we bring a problem to an electrical engineer and we provide enough information that they can solve it, we've shifted our language into, we found this problem or issue, or as we would say at HP, opportunity was another term we often used, that will help us achieve our 98% over 2-year goal. Right now we're at 95% success rate, and we want to be at 98% success rate. So if we solve these 3 things, we'll be a lot closer to getting there. But it's a subtle change in our language, but recognizing that the people we work with are often working to make something work. They're in the success space, and we're often looking at, well, how can it fail, which isn't the way they want to view the world, even though we're oftentimes violently agreeing. Let's see. Yeah, exactly right. In this comment is that a lot of our work is to help people make informed decisions, and reliability is a lot harder to measure in many cases than time to market or cost or functionality. And so we work to help people get the information they need in order to make these decisions. Now, I often say that reliability occurs at the point of decision, right? It's not just the design review at the end of the line saying, hey, it's good enough or it's not good enough. The reliability occurs when we decide it's going to be plastic versus metal. It's occurs when we decide there's going to be this technology versus that, where it's going to have redundancy or not, whether it's going to, what sets of functions is it going to have, and how likely are we able to design those in? How are we going to assemble it? Which vendors we're going to use? And then is this capacitor get located here or over here? One of them's a little closer to a screw that mounts the circuit board, which deflects the board, which has the potential to crack that capacitor, that multi-layer ceramic capacitor. If I move it just a little further away, it has less of a chance to fail. Now, we could spend the time to figure out exactly what that change in failure rate is. And we often don't. We put those kinds of things in layout guidelines and keep out zones and things like that for a range of different reasons. But it makes a difference. And it's that decision, that kind of detailed, finite, very peculiar little decision. Do I put it here or put it over here 10 millimeters away? That can make a difference in the reliability of your system. And there's thousands and thousands of those decisions that occur in not just the designer area, but in the manufacturing team and in the suppliers teams and your vendors teams and your warehousing teams and installers and how it's used and how we understand how it's used. All of those decisions affect the resulting reliability. There's no way we're going to be involved with every one of those decisions. Yet a big part of what we do is set up structures and infrastructure and culture that affects all of those decisions, right? We create systems that allow people to understand the importance of, you put the capacitor here or here, for example, or what questions to ask vendors, or how the impact of material change affects based on the environment that we're going to be in. A big part of what we do is focus on decisions. And those decisions are aimed at providing sufficient information and structure so that they can consider the impact on the reliability or on avoiding failures. All right. Yeah, and you're exactly right, Lana. One of the things is that we work with decision makers and at all levels of an organization. And it's our ability to influence them and to guide them in creating derating guidelines, for example, and training people on how to use them, or sharing how things fail, the failure analysis that we're seeing from field failures, and conveying that information across the organization in a way that we all can learn from it. And it's part this particular failure mechanism, but part is how could we have avoided this? What's our long-term structural change that allows us to avoid these problems? So there's lots of different ways we can influence decisions. Now, a key part is to understand which decisions are being made, right? If we're setting up to do an accelerated life test, well, when do you need this results? It might be a basic element of when somebody needs to make a decision. It's essentially how I got started in reliability engineering. They said, we need to know if this is going to last for 20 years, and we need to know it in 6 months. And I'm like, okay, well, that means I have to do an accelerated life test, which I don't know how to do. So I went and figured that out, and then essentially at that point, started a career in reliability. But I was able to provide the results of that accelerated test that gave the decision makers additional information about the expected failure mechanisms and how likely they were to fail over a 20-year duration under particular circumstances, under a particular environment. And then they use that information to make the decisions to go forward with that product or not. And they did, actually. The product was actually very durable. Looking at the comments here. All right. I think I've got another question for you. So what would you say are the top 3 sources of failures? Say in a generic sense. You don't have to pick particular failure mechanisms, but what are 3 sources of failures? Yeah. And Andre, I wanted to take another look at your comment. You're exactly right. It's heading in the right direction is oftentimes the best we can do. And that is, part of influencing these decisions. If it's just ignored, or we don't measure that, or we don't have any feedback on that, or that's too difficult. There's some of the many excuses we hear about even measuring or estimating reliability. And without that feedback, we don't know if we're getting better or worse. But we can also narrow it down to just best practices and good sound engineering principles and understanding the phenomena of the failure mechanisms and making sure we're making design decisions that mitigate or avoid those problems, right? Um, the idea is that we can cause influence, or we can influence a very large organization by being very focused on that's part of what we do. That's what we're there for. It's not to take the blame when something goes wrong or just do failure analysis. It's, well, how do I avoid these failures? How do I mitigate these things? How do I get a system in place so that these failure mechanisms just don't have the chance to occur at the rate they're occurring? All right, so I'm going to look at some of the questions for sources of failures. Now, insufficient testing. I would disagree with that. Testing is kind of a last resort, and testing doesn't create a reliable product. It gives us a reflection of is it reliable or not, if it's a reliability related test. But testing in and of itself is a feedback mechanism, right? It's not the source of the failure. The failure doesn't occur whether we test or not, right? We can design a product, never test it at all, and it can work just fine, or it could fail miserably in the field. Testing would have helped us decide, is it good or not good? But it didn't actually create the failures, right? Assembly, human factors, and usage. All right, good. I would have added engineers, lack of redundancy. Now, a lot of things we don't want redundancy. It's too expensive, so we don't do it. Like your iPhone probably has very little, if any, redundancy. Inappropriate materials, that's closer to what I'm looking for, is in the design area. Yeah, everything can cause failures. Yeah, that's true. I like that comment. Andre's incorrect operation, incorrect design, lack of maintenance, and so on. Yep, all good. Design margins or limits, over design. Now, so let me share these out. Now, there's lots of ways we come to failures, but it's usually a decision, right? We decide to put that capacitor closer to the edge, either out of ignorance or that we had no options, or it was a calculated risk and we decided to do that. But then we find that in assembly, they weren't aware of that trade-off. And so they decided to bolt it down like they normally do and ended up cracking those capacitors, leading to those systems failing. By the way, that's actually a real case that I ran into some years ago. So it's kind of vivid for me. But almost all of the sources of failures are decisions. I would say second is material variability, right? The variability of our processes of creating the substances that we use and the assembly processes that we use would be two key pieces of those. And then customers using our products in completely unexpected ways. Adam Barrett's he's got this use case 7 campaign going, where he talks about you got to think through all the ways people can misuse or use your product. And the simple example is if you got a wrench in your hand, but you need to tap a bolt through an opening, a small hammer would be the appropriate tool, but you have a wrench in your hand, so you tap it with the wrench. I can imagine most of you have done this at one point or another. If you do that a lot, you're going to cause your wrench to fail, right? It will not be aligned anymore. It'll be rounded over. It'll do all kinds of other issues. It might even break because it's not really set up to withstand impacts like a hammer is. And so the idea here is that there's lots of ways that we can have failures occur. right? But they really narrow down to a couple sources, and decisions and variability are two part of it. And so the last set of info here is we're not just in the influencing role. We also have a leadership duty within our organizations, right? First off is back to my electrical engineering buddy that I worked with early on, is problem solving, right? We get to do engineering. We get to run experiments. We get to understand failure mechanisms and process variability, for example, in such a way that allows us to find solutions, to come up with problems. Now, we may not have the engineering chops to get into the details of what are the reasonable options to consider, but we certainly can lead a team of people to find that problem, to solve those problems. You know, the Six Sigma black belt type activities is pull together the appropriate team and help them solve the problem. And by going, it's one of the things that we do that very few other disciplines in the product development and maintenance world have the luxury of, is we get to cross silos. We'll work with software, hardware, human factors, marketing, finance, and so on. And we get trained in failure analysis and understanding failure mechanisms. And if you're really good, you get a lot of experience and training on leading a team or leading a meeting, creating a collaborative experience for folks to, even if it's just doing FMEAs, we need those meeting management and group dynamic type skills in order for it to be effective. But we get to solve problems. We get to go work with people to implement, find issues, create solutions, and implement them. And for me, anyway, that's a lot of fun. And we can take a leadership role in making those happen by facilitating those things in happening. As I mentioned, we have a unique view. When I first started in reliability engineering, I was working on really on inkjet printers. The senior project manager was a senior manager within the organization and had managers for electrical engineering, mechanical engineering, software engineering, marketing, and supply chain, and others were all these managers that had teams of people working for them, and me. I had no team. It was just me. And I got time with the senior person just like all the other managers did. My input at those meetings carried as much weight as the electrical engineering team managers did. And I was just an engineer, first level, assigned to this project. No, and it was my first assignment within the organization. Yet I was given a lot of deference and asked questions that often went across all of these other teams. And sometimes I'm talking to executives, and then the next hour I'm talking to the technicians on the shop floor trying to make this product. And then I'm on the phone with the supplier in Asia, and then I'm on a phone to a supplier that just showed up. And then we even got to talk to customers. There's very few, if any, other positions within engineering that gets that breadth of exposure and influence. And I think our leadership role is recognizing that we do get to do this. We do get to go from board level to customer to technician. And we can influence the decisions that all of them make. And that's, I think, keeping that in mind is a unique feature of what we do. And there's very few other parts of the organization that do that. And the really bottom line here of one of the things that I think is crucial to being a reliability engineer is that we have to add value. And I know I've done webinars on this. I've got a short ebook that's out on this on Accendo. But the idea here is that everything we do it has to add value, where it's conversations, it's training, or it's setting up structures or guidelines, or it's problem solving, or asking questions, or whatever it is that we do. Each and every one of those things we do should contribute to the ability of others to do their job well and to create a product that actually meets customers' expectations, right? And within your organization, value may be defined as time to market, or it might be cost, or it might be quality, or it might be low failure rate, or a mixture of all of those things. And so, but there's many ways that we can add value rather than just focusing on, well, I need to run this halt test today and get this report to Jeff by Friday. Well, let's make sure that that report is actually going to be contributing information that Jeff needs to make decisions. That's an extra step, but that's where the value comes from. If that report goes over there and never gets read, it has no value. But if it goes to Jeff and Jeff gets his team together and says, hey, we need to solve these 3 problems because I understand them now and they're going to cause us problems in the future, let's get on these things. That adds value. That changed the behavior of Jeff and that team. We can focus on failure rate reduction or reducing the risk of a delay in the program by finding issues earlier versus later. We can focus on customer value and what is it that they need and how do they use the product so that we can design a product that meets those requirements and so on. There's lots of ways we can add value. But the point is that we need to do that with every interaction, with every step of every day that we take, right? And so if you're being tasked to create an estimate, well, who needs it and to what degree? What's it going to be used for? And how can I create an estimate that is informative and useful for them to make a decision? That's adding value. So it really cuts down the chase. So I'll leave you a rhetorical question here at the end. Let me take a look at a comment. The last problem-solving effort. I work hard, such management urgency that management did not support a disciplined approach. Any suggestions? Well, it's one of those old adages, and it's one of those things where you have to have enough trust to be allowed the time to get it right. Whereas I also found that if after the fact, if you say, well, I told you so, we solved the wrong problem because of the urgency of this, and we're now solving it again. There's that old adage of, pay me now or pay me later, is, well, we don't have time to prevent the problem. We seem to always find time to resolve the problem. And it's way more expensive resolving it. Now, we can say, I told you so, but it doesn't really work. So I don't recommend that approach. The idea here is to say, is to make the case to solve the real problem. And that's easier said than done. Is if we actually understand the problem, we have a much higher probability of actually solving it or preventing it. And as you get the opportunity to do the appropriate problem solving and due diligence to get it right, is quantify how useful that was, as opposed to the shotgun approaches that we often take and how often that actually works. Is just keep track, keep a scorecard on it. And then you create the data set that says, here's the evidence. When we do it using the 8D method, we solve the problems 95% of the time. If we just go jump to the first solution that comes to mind and hope it works, we're at a 60% success rate. You do the math. Here's where the value is one of the suggestions. Every situation will be a little different. It often helps to have a good champion that understands the premise of all this stuff, but it's chip away at it and create the space and the trust that the due diligence kind of process is more valuable in the long run. That'd be one way I would make a way to do that. Okay, so I think in summary, as I'm coming up, just over my time limit, keep in mind that a lot of what we do is dealing with failures. Is one would say is it keeps us in business, right? We have to deal with failures. The key is that we need to understand those failures. It's not just us. We need to help the rest of the organization, those people that we want to influence, to understand those failures, the failure mechanisms. Our role is an influencer. Think of yourself as a consultant, right? You don't get the final say, but you certainly can shape the information that frames the questions that have to be answered. And we also have a role in leadership. You can take on that role as often as you feel comfortable, and the more you do it, the more effective you're going to be. The the fewer failures that happen. And then we work on the culture to create a culture that avoids failures for our customers and for our systems, because we have that fundamental culture of celebrating failures when they do occur, or looking for them so that we can continue to learn. So that's my pitch for today. Thanks so much for attending and contributing. I am actively looking at Zoom Webinar as a platform so that we can get our chat window working. I really miss having the ability for attendees to chat with each other. And so I'm thinking about doing that. If you've got experience with Zoom webinar platform, please let me know. I'd love to pick your brain a little bit about what's working and not working in that, and how it would be different than what we're using now. So with that, I'll stay on the line if there's any follow-up questions. But I think I'll go ahead and close out the recording. And I, as usual, completely forgot to pull up what I'm going to be talking about next month, or even what's on the docket for next week. You can find that at Accendo Reliability underneath webinars, and open the menu for upcoming live webinars. And we'll see you next week, and if not, next month. Talk to you all later. Enjoy the rest of your day.